So moving on, a little bit about Forterra. We are, as Cheryl mentioned, the largest precast concrete pipe and drainage manufacturer in North Dakota. We design and provide solutions that apply to water supply, wastewater, drainage, highway, airport, railroad, and even trenchless applications as well. And some of the products that we have that go toward that include pipe, box culverts, bridges, catch basins, and many other precast concrete products as well. So what we'll be going over today is more or less we'll start with the definitions of sustainability and resilience and work off of that. We will apply those principles to see how resilience and risk relate, as well as how sustainability applies to the environmental, social, and economic aspect of our world. In other words, the triple bottom line. At the end, we will provide a summary of everything we talked about as well. But briefly, before we get to that, I want to go over some foundational principles. First off, we can ask the question of why do we need drainage infrastructure? The best answer to that is namely because it rains. It can rain on mountainous terrain and flow into the lower grounds, and this also affects our cities as well. If the rainwater that amounts over time is not taken care of, it can result in foundation damage, significant flooding, or even trash and debris buildup within our cities. When it comes to urban runoff, comparing that to rainfall that covers natural ground, you see that 10% of the water on natural ground goes to runoff, and 50% goes to infiltration. It is able to seep into the ground. When you look, on the other hand, at the high density residential, industrial, or commercial in the lower right picture, you can see that 55% of that rain goes to runoff. And this is where you have the increased risk of flooding, foundation damage, or standing pollution. And so drainage infrastructure comes along to take care of that in an organized way, to protect the foundation damage, to protect against foundation damage, and carry the surface runoff into the underground storm drain system, and is able to carry that directly to waterways. Just a technical note as well, there's the difference between our underground systems is we have storm sewer or drainage, as we call it, and this is differentiated between sanitary or wastewater systems as well. And so there are two different approaches to handling the water that needs to be taken care of to benefit society. For culverts as well, these end up assisting in protecting the foundation for roadways. On the left side of the screen, you can see what we call a double cell box culvert. These are for applications where you have a lot of water running underneath a roadway system. For smaller applications, you see the picture on the right, and this is an example of minor drainage that needs to prevent erosion of the highway or road foundation. And so looking at the pipe itself, you need to see what functions that the pipe should be able to perform. First of all, it needs to be able to carry a load. And so the examples that we have are the earth load, the live load, which are an example of that is cars running over the top of a highway. You also have construction loading, as they are compacting soil and moving heavy equipment over the installed pipeline. The pipeline needs to be able to carry those loads over the duration of its lifetime. The second thing that a pipe is meant to do is serve as a conduit. It needs to allow water to pass through it. And these loads as well are based on AASHTO HL93 from the LRFD Bridge Design Manual as well. And we have a link here to direct you to a place that provides more information on that. Another thing I want to highlight is there are multiple kinds of pipe as well. There are rigid pipe and there are flexible pipe, which have a completely different design approach when you are analyzing the loads that they experience, as well as the way that they provide a conduit for water as well. For rigid pipe, it does not bend. The technical definition is that it is able to deflect less than 2% without cracking. For flexible pipe, it is designed to bend. The technical definition for that is it is able to deflect more than 2% without showing signs of cracking in the pipe wall. Rigid pipe is typically very heavy. Whereas flexible pipe are usually very light. The examples that we see with this are plastic and metal pipe, and rigid pipe are going to be your reinforced concrete pipe, which we're talking about today, and your vitrified clay pipe as well. And so those are the two most common examples of a rigid pipe. Rigid pipe also provides high strength. Whereas flexible pipe relies on the soil strength and the quality of installation. Rigid pipe, due to its weight, has a very low risk of flotation, which we'll talk a little bit more about in this presentation. Whereas flexible pipe, because it is so lightweight, has a high risk of flotation as well. And these are just some visual examples of what the rigid and flexible pipes may look like. And so we'll skip questions for now and go directly into the presentation on sustainability and resilience. So why are we here? Why are we talking about these topics? The main reason that we're looking at is this is a forward-minded aspect of civil engineering. The generations of the future depend on us making responsible, resilient, and sustainable decisions today. And this is ultimately the part of the legacy that we leave behind us. What does sustainability mean for you? Some things that might come to mind may include long-lasting, harmonious, eco-friendly, existence, symbiotic, quality of life, efficient, LEED certification, green, environment, society, economy. But the definition that I want to look at for sustainability is simply this: the ability to exist continually, or a more common one, meeting our own needs without compromising the ability of future generations to meet the needs of their own. Many people primarily associate sustainability with environmental considerations, but the core concept of sustainability encompasses much more than that. If current practices are carried out without change for decades, centuries, or millennia from now, will societal systems remain functional without eventually falling apart? If you put it as a statement, if a system is sustainable, it will theoretically remain operational without negative effects to its own functionality, or the systems looking around it throughout the test of time. Sustainability is looking at everything with a long-term lens. Traditionally, sustainability is categorized by societal, environmental, and economic sustainability. These categories encompass what is referred to as the three pillars of sustainability: the triple bottom line, or people, planet, profit. It's important that every transportation, housing, power, water, waste, and drainage system be constructed with all three aspects of sustainability as a top priority. Doing so will ensure a higher quality of life for generations to come. Engineers and decision makers must not only be focused on meeting the needs of our communities today, but tomorrow as well. And so from here, I will also ask, what does resilience mean for you? Some things that may come to mind are resistance, limiting impacts, response to adversity, durability, toughness, flexibility, or robustness. The definition that we're using today comes from AASHTO, or the American Association of State Transportation Officials. Resilience is defined as the ability to prepare, plan for, absorb, recover from, or more successfully adapt to adverse events. Because of the present threats that our infrastructure system faces, sustainability should always be coupled with resilience. Infrastructure that is sustainable and also not resilient will inevitably fall because it cannot adequately resist disturbances and will require frequent repairs or replacement. Resilience should thus be seen as a necessary supporting element of sustainability. And so in short, I like to think of resilience as a Rocky Balboa quote when he said that it's not about how hard you can hit, it's about how hard you can get hit and keep moving forward. According to the US Resiliency Council, in a 2016 study, they indicated that many LEED certified buildings in Superstorm Sandy were designed to have a low impact on the environment, but not for the environment to have a low impact on them. Let's take a look at how a resilient system reacts to an adverse event or stress compared to a non-resilient structure. Our chart here shows the performance of the structure against the timeline across the x-axis. The green line is our pre-event performance. Culvert A, let's say, is flowing along nicely prior to any stressful event. Now let's introduce a stress on the system, say a major storm event. In this case, the performance of the system has dropped due to the flood. Perhaps the roadway system was damaged or the head wall experienced scour. While the performance takes a hit, this resilient system experiences only a brief recovery phase and disruption while crews work to bring it back to pre-event operational levels. But what happens if our culvert isn't resilient? Well, we would expect the performance level to drop significantly during our hypothetical flood. Maybe the pipe backfill washes away and the culvert floats down the stream. In this case, our recovery time is much longer and the amount of energy needed to bring the system back to pre-event operation is much higher. So how can you measure resilience? One of the keys to understanding resilience is looking at risk. If you've ever heard of the Argonne National Laboratory, they were the first laboratory in the world to create a self-sustaining nuclear reaction in a small project known as the Manhattan Project. After World War II, this project continued and began developing energy rather than nuclear bombs. However, they recently developed a tool for measuring resilience of particular systems by introducing a resilience measurement index. A large part of this index involves evaluating the risk of a particular system. In their report, they identify that risk is at the intersection of threats, vulnerabilities, and consequences as shown in the Venn diagram. Here's another way to view that same concept. Ultimately, consequences are what you're trying to limit and avoid, but consequences are a result of threats matched against a system's vulnerabilities. Let's take a closer look at the risks involved with drainage infrastructure. We'll begin by dividing these threats into natural and unnatural threats. Flooding is an obvious issue in many places. Extreme temperatures can cause expansion and contraction of various pipe materials. Severe rain can lead to flash flooding. A tropical cyclone, which is a growing concern in many coastal regions, and wildfires as well. While California gets the bulk of the attention, Montana had the largest acreage burned out of any state that experienced severe wildfires in 2021. Winter storms as well, which is what we're experiencing right now in South Dakota, can bring ice and freezing temperatures that cause additional concerns. Now let's look at unnatural threats. Litter and debris can cause culvert clogging and other damages. Vehicle accidents, you can think of highway fuel spills and where those liquids end up going. Poor installation. This is one of the biggest issues facing flexible pipe installations. And other issues may include vandalism, excessive loading, etc. The National Center for Environmental Information tracks billion-dollar weather disasters. This data traces back to the 1980s. The total cost of these natural events has been increasing over the past few years. Resilience seeks to arm our infrastructure to minimize the impact of these natural disasters. Here you can see the billion-dollar disasters that took place in 2021. The Western wildfires that I mentioned certainly made a huge impact to the area where I'm from. This is also compared to the billion-dollar disasters in 2019 as well. What kind of vulnerabilities may there be towards drainage infrastructure? You can have culverts without a head wall, or if the head wall is missing proper reinforcement, they then become susceptible to washout and piping. Flotation may be a vulnerability as a combination of pipe weight and cover over the top of the pipe. Certain pipe materials and coatings may be prone to catching fire. Deficient joints may lead to excessive infiltration and void formation beneath the surface. Poor installations are certainly another concern. Issues in this area can be avoided with proper inspection before and after installation. Consequences are then our potential negative outcomes. And so from here, we'll talk about some specific cases of where we see the consequences play out. I don't know if you're able to hear the video on this, but here we see a number of examples of storms as well. These may include 100-year, 500-year, and 1,000-year storms.
Oh my God! I just don't look all that water. That is crazy. Thank you, Lord, that I got off of it. I just flew just in time. I'll get one right over there. Woo-hoo-hoo! Look at that crap. I don't know if you can see something like this over there. I was parked right over there in the water. I think they're cracking up right there. Thank the Lord.
It's really amazing what water can do. Another example comes from a colleague of mine in Georgia, where the road had washed out over a creek during a storm. 3 of the 5 pipes that are shown here, sorry, 2 of the 5 pipes that are shown here washed out along this roadway. This was a cul-de-sac leading to over 10 homes. During the duration of the storm, this entire subdevelopment was left without access to an escape route or food, and the ability to move in and out of their homes. This area that washed out was called Garner Creek, these people were left stranded until the proper repairs could be made. Downstream from the washout, my colleague was able to find fragments of this corrugated metal pipe. As you can see from the corrosion, this pipe had failed long before the flood ever happened. The repairs made at this crossing used a triple barrel box culvert. You can see the one on the right side is set at a different elevation to prevent sediment buildup in the other 2 boxes. Remember the graph at the beginning that showed the differences between recovery times of resilient and non-resilient infrastructure? This is an example of the latter. It took a long time for these boxes to be put in and for the people in the subdevelopment to have access to leaving the area of their homes. The primary hope in managing resilience is that something like this never happens. However, because reinforced concrete pipe is naturally resistant to flotation because of its weight, it allowed for significantly lower repair times than what happened in the previous example. Instead of entirely replacing the pipeline and the road over the pipe was able to have additional backfill placed over it, and the base course laid and pavement re-put. The Santa Rosa fires in California in 2017 ended up burning more than 5,000 homes and killing 23 people. City codes required the last 20 feet to be constructed of a corrugated metal material in order to avoid fire risk. This is a post on social media from the Department of Transportation in California, where they asked what if we ever wondered what happens to plastic culvert piping when a wildfire is burning everything around it. Some culverts along various routes liquefied from the heat of the fire. In the first two photos, the plastic piping sits in a puddle at the bottom of the culvert. The earth around the culvert retains its shape. In other cases, the pipes partially melted, impacting drainage and the integrity of the culvert. Another example comes from Paradise, California. Wildfires can significantly endanger a piping system, and because they are so critical to the support of the road and various escape routes or evacuation routes, it's critical to have a pipe that is resistant to emergency disasters. Another thing about plastic piping is it releases volatile chemicals such as benzene when burned. Benzene is a carcinogenic hydrocarbon associated with crude oil that's strictly regulated by the EPA. Even if a building survives a wildfire, breaches in the system miles away can still contaminate its water. Another example comes from Stoneburg, Texas, where a wildfire ignited a triple line of 60-inch diameter high-density polyethylene pipes. The road collapsed as residents were attempting to escape the flames. Emergency vehicles ended up nose down in the ditch as well. And this resident, with his pickup shown there, ended up totaling his vehicle, and the driver ended up being injured. One of the two evacuation routes in Stoneburg during this fire were closed as a result. Given the disastrous effects of the fire, the Texas DOT implemented a number of restrictions. Plastic pipe was not able to be used under roadways with a current annual daily traffic less than 2,000 per lane. The inside pipe diameters could be no greater than 36 inches. Multiple pipe installations were limited to a maximum of 2 adjacent pipes. And for pipe installations beneath and adjacent to roadways, they were required to provide precast concrete safety end treatments as well. So this ultimately goes back to show that consequences are a result of vulnerabilities matched against their threats. Threats are ultimately inevitable, although some aspects of environmental sustainability seek to reverse the trend of those threats for the foreseeable future. We will be forced to deal with these threats one way or another. Consequences can also be limited by planning and reactive measures, but reducing vulnerabilities is perhaps the most effective way to limit or remove consequences from threats. Resilience is ultimately about mitigating risk. When it comes to drainage systems, designing resilience will limit system vulnerabilities and in turn reduce or eliminate potential consequences. Concrete pipe provides inherent resilience that is unmatched by any other pipe material. Reinforced concrete pipe provides the primary structure, and is resistant to insulation issues or loss of support material. Concrete pipe is the only pipe material that has a proven performance of 100 or more years for its service life. Concrete pipe is rigid, and that makes it and that provides for high tolerance joints that ensure a dependable seal. Reinforced concrete pipe is also inherently non-flammable as well, and its high weight reduces the risk of flotation. More decisions are being made today on the basis of environmental sustainability than ever before. Environmental sustainability includes a whole gambit of categories, such as air and water quality, waste, pollution, and fresh water use, but most people probably think of climate change first. This is primarily measured by looking at greenhouse gas emissions. Each of the pillars of sustainability provides a unique facet to our quality of life. But as we move into this section, let's keep in mind that the foundation of this sustainability is resilience. As with any structure, if it isn't built on a solid foundation, it doesn't matter how strong your pillars are. If you've ever heard that if concrete was a country, it would be third in the world in terms of emissions. However, concrete itself has actually relatively low emissions. The reason we hear the total emissions are so high, of course, is that there are 10 billion tons of concrete used every single year, which is more than 5 times as much as any other product material. Concrete is also the most used material in the world next to water. However, we can still do what we can to limit emissions. But remember that concrete is a gigantic part of our infrastructure. If we want to look at the sustainability of a particular material, we need to compare it to what an alternative product would look like. Here, it is immediately evident that concrete pipe has the lowest emissions factor on a per weight basis than any other pipe product. Compared to HDPE pipe, reinforced concrete pipe emits less than 1/10 of the equivalent CO2 per unit weight. 75% of concrete's makeup are raw natural resources, such as rock, sand, and water. So it makes sense that it has the lowest emissions of almost any material. However, if we factor in the pipe weights for a given size, the per foot emissions for RCP are still less or comparable to some of the other common drainage products. To be fair, the higher weight of reinforced concrete pipe is providing resilience and structural performance that simply cannot be matched with other products. Many studies only evaluate the cradle to gate emissions, meaning they only include up to the point where the product is ready to be shipped out of the factory where it was produced. This is really only a fraction of the whole picture. A comprehensive look at total emissions related to drainage pipes shows concrete pipe as the most sustainable material choice. Reinforced concrete pipe has the lowest material emissions, which we just looked at. Reinforced concrete pipe also recaptures carbon dioxide over its lifetime. It's well documented that roughly 50% of cement emissions are recaptured over a 100-year span of concrete. For RCP, that reduces net emissions by 25%. For transport distance, the American Concrete Pipe Association has over 200 plants in the US. Plastic pipe, depending on the material type, has less than 50. Plus, they typically provide through distributors. Direct shipments mean less miles on the road and less emissions. Imported fill emissions, volumes based on AASHTO, the volumes are based on AASHTO trench details. The structural backfill must not only be mined and shipped in, but excavated backfill may need to be shipped out as well. For the service life, many sources have documented reinforced concrete pipe with a 100-year service life. Corrugated metal pipe is lucky to get 50 years. The jury is still out on plastic pipe, but sources such as the Army Corps of Engineers are hesitant to give it anything above 50. For reuse, reinforced concrete pipe sections can either be reused or broken down and recycled as crushed aggregate at the end of their service life. Many coastal regions as well use it for reef restoration projects. For freshwater demand, according to Plastics Europe, they released a report that described an environment that had an environmental product declaration for reinforced concrete pipe, noting that it had significantly lower water demand than plastic pipes. Now we'll move on to economic sustainability. To account for environmental sustainability, we need to take into account not only emissions to the point where the product is ready to be shipped out of the factory where it was produced. The overall life of the product must be evaluated. The factors affecting the economic sustainability are also based on a complete life cycle. Short-term costs may look appealing to entities who are looking to make their budget each year. That can cause a burden on future generations from maintenance and/or replacement costs. Let's compare this to purchasing a new vehicle. Purchasing a new vehicle that has the lowest upfront cost may seem like a wise decision based on your budget at the time of your purchase. The upfront cost of a car is not the only cost when we talk about the total cost of ownership. Going with the cheapest sticker price car may mean more expenses in areas like insurance, maintenance cycles, unforeseen mechanical issues, or even just the life expectancy of the car. Spending extra dollars on a more durable, proven vehicle will often offset the additional costs and provide the lowest cost of ownership in the long run. Now we can apply the principle of economic sustainability to infrastructure. A desirable, economically sustainable infrastructure means that as a community grows, the economic resources necessary to build new systems and maintain or replace existing systems will be retained at a manageable rate. For this to be achieved, designers and decision makers must take life cycle costs into account. The life cycle cost analysis is an analysis methodology that enables decision makers to better understand the economic impacts of infrastructure over its service life. According to a study by ASCE and the ENO Center for Transportation, only 59% of governmental agencies across the US employ some type of life cycle cost analysis. Typically, when they do, they are related to pavement materials and go no further. Moving towards economic sustainability means applying this methodology to more things. Now we can break down each of the categories within this equation. We'll take a closer look at the initial construction, the maintenance, as well as the service life. Beginning with initial construction, the initial cost is made up of pipe material cost, as we called it before, the cradle to gate cost. This is what is most often used as the basis of cost, but there are more factors that needed to be added when calculating initial cost. Installation materials and methods cost. Installation is directly linked to the structural behavior of the pipe. And then last but not least, the cost of inspection. Different pipe materials will have different requirements for post-installation. Without proper construction inspection, an improperly installed storm sewer or culvert will likely require more maintenance than it would had it been properly installed. Some examples of this may include proper joint connections, proper bedding preparation, and the compaction of haunch and backfill materials of the pipe. Typical maintenance items, such as cleaning or jetting of the line from debris, fixing or repairing sealing individual joints or deterioration in a pipeline, or the lining of the pipe when deterioration cannot be fixed. When calculating maintenance cost, local trends should consider, since each local market and agencies, when calculating maintenance costs, local trends should consider maintenance cost, since each local market and agency has its own unique characteristics. Routine inspections can catch small issues before they become big issues. Many bridge and culvert failures have been avoided because people flag the issue before something catastrophic happens. Routine inspection also allows entities to track culvert condition over time to estimate a rate of deterioration to help with planning. Some pipeline rehabilitation projects, while pricey, may effectively extend the service life of the pipe beyond the original service life estimate. One of the things to look at when it comes to service life is the actual service life of the product versus the promoted service life of the product. Manufacturer claims, including those of reinforced concrete pipe manufacturers, should be checked against third-party sources when calculating service life. The National Cooperative Highway Research Program, Army Corps of Engineers, as well as the Army Corps of Engineers, published a table of expected culvert life expectancies for different materials for most conditions. You also have the local experience and conditions. Agencies can use its own local data to calculate an actual proven service life of a pipe instead of using a theoretically provided value. One great example of this is a report put together by the City of Olympia in Washington, where they look at their own data to determine life expectancy of culverts and to determine true costs of each material life. You also have pipeline construction inspection. A properly inspected culvert will likely last much longer than one that is not. Issues or shortcuts in the construction of the pipeline may not surface until long after the contractor is gone. You also have the residual value of a pipe. The American Society of Testing and Materials has LCA practices for 3 of the available pipe materials: concrete, plastic, and metal. Flexible pipe standards focus on the terminal value of a pipe, given that flexible products are hard to be removed without damaging or deforming the pipe, making it harder to reuse. Rigid pipes, on the other hand, focus on the terminal value in terms of reuse, since its structural performance allows, in many cases, for the pipe to be removed without damage and then can be reused on another project. So in summary, reinforced concrete pipe has an incredibly high initial value. When concrete pipe is purchased, the contractor is getting a structure delivered to the site. Because the majority of the structure lies within the pipe itself, concrete pipe has the lowest installation costs associated with proper placement of structural backfill around the pipe. Not only is the structural backfill only required up to the spring line of the pipe, but the smooth exterior of a concrete pipe means you don't need to worry about the extra work that is needed for working backfill into and around corrugated exteriors. Concrete pipe also doesn't require mandrel or laser profiling to be completed as verification of the soil structure. Concrete pipe has the highest proven design life in the industry, and we are confidently proud of that. Concrete pipe is durable enough that in many cases, at the end of life for one project, it may still be acceptable to remove and reuse the pipe on another project. This residual value is an important economic consideration. All of these things make the concrete pipe a true economically sustainable product. From here, we'll move on to societal sustainability. The performance of our infrastructure is critical to the function of our communities. The American Society of Civil Engineers surveys the condition and functionality of infrastructure systems of different states and the country as a whole. One of their latest ratings, given in 2017, gave the United States a D+ grade overall, with a score of D for roads, D+ for wastewater, and a C for bridge. Recently, they improved that score to a C-. However, this still illustrates the need for resilient and sustainable infrastructure and shows that it is more important than ever before. With that being said, we also see an uptick in natural disasters around the world. The image on the right shows an estimate on how many people are affected each year by floods, hurricanes, earthquakes, and fires. According to the National Centers for Environmental Information, the United States was impacted by 14 separate billion-dollar disasters in 2020. Out of those, 12 were water or fire related. These disasters are only made worse if they cause underground infrastructure to fail. Consequently, when it comes to the drainage industry, members of society are called on to rely on infrastructure that they will rarely have to see, think about, or take notice of. At least, not until a failure occurs that significantly impacts the way of life, health, safety, or well-being of those we serve as engineers. More than ever, we need to be designing infrastructure with this thought in mind so that we may ensure the communities we serve also face natural disasters in the most resilient way possible. As I mentioned before, our industry creates a product that the public rarely notices. Usually, if they do, it means something is wrong. Drivers rely on roads every day to get them to where they need to go. For the infrastructure that helps support these roads, it should also be our goal to keep the driver's peace of mind intact when choosing the right pipe. At the end of the day, it is this aspect of trust that allows our society to be sustainable. Without it, it can result in a significant detriment. But with it comes an established long-term benefit to our communities as we press forward together toward a sustainable and resilient future. However, this isn't just the responsibility of the engineer. Pipe systems should be designed to be reliable. This means that when a pipe is installed in the ground, it ought to remain unseen for generations. However, to achieve this end, it isn't enough to simply say that one kind of pipe should be installed in all cases. There ought to be a more universal focus on resilience through the perspective of individual users, political leaders, and engineers. A long-term vision of resilience and sustainability in the policies and design standards requires action by all the stakeholders involved. As resilient infrastructure works to uphold sustainability for the planet and economy, so too do the stakeholders work to uphold sustainability for society. The three main stakeholders are as follows: your individual users, the infrastructure designers and operators, and the policy actors. All three functions have their importance on the resilience and sustainability of the system. Individual users are the people that enjoy the benefits from a reliable infrastructure, but also those that are affected the most when it fails. Their input is important to form a clear message that will be heard by policymakers. Our city councilmen and women, mayors, legislators, and governors are those we have trusted to make the proper policy changes. As a result, policymakers shape the regulations. They are the ones that will plan and manage all the aspects of community recovery by taking action on the current event, while also making sure similar damage is not repeated in the future. Changes to and application of the codes and standards will be followed by the third function, the designers and operators. However, the policymakers will be the ones that make flooding requirements mandatory, which also allow the designers to create resilient structures that will, in turn, improve the life of the citizens of that community. When we don't design for a sustainable infrastructure, it means we are only solving permanent problems with a temporary fix. To combat this, all functions of the society ought to be well educated in terms of how infrastructure affects the health and sustainability of the communities we live in. To accomplish this end, we as the designers and operators must know the impact that inadequate infrastructure can have on society, as well as how resilient infrastructure provides the solution to not only the ethical responsibilities, but also as a means of improving the livelihood and well-being of the communities we serve. So as a recap, remember the why of sustainability. Sustainability is the key to building a brighter future for our families and our communities. What we do today affects tomorrow. In terms of environmental sustainability, this means being conscious of our world and the environment we live in. Namely, how does our infrastructure impact air quality, availability of clean water, land use, waste, and obviously long-term climate change? For economic sustainability, it means looking beyond this year's budget and evaluating true cost of ownership. For societal sustainability, it means limiting delays and improving social convenience while keeping user safety a top priority. Lastly, an integral part of sustainability is ensuring that our infrastructure is resilient enough to resist and defend our communities from present and future threats. Let's invest in a more robust infrastructure today so that we can save resources and headache in the future for ourselves and others. And finally, sustainability and resilience need to be an integral part of how our infrastructure is built. Reinforced concrete pipe boasts some of the most sustainable and resilient features of any pipe product. When considering full life cycle impacts, reinforced concrete pipe is the most sustainable product and is also inherently resistant to flooding, fires, and other threats to drainage infrastructure. This helps to improve user safety, convenience, and overall quality of life. Concrete pipe has been and continues to be a key tool towards building sustainable and resilient communities. And with that, I will take some time to look at the questions.
Thank you, Joseph. I don't see any questions in the chat room right now, but if anyone has questions, you can feel free to unmute yourselves. I just wanted to thank you for this really informative presentation. And the recording of this will be posted on our website and will be really useful for our center. So we're really appreciative of that. And as soon as I post this, I have to do a little bit of editing. I will inform our audience. And Joseph has also offered up his contact information for anyone who might have questions. So feel free to speak up if you have any questions for Joseph.
Yeah, I have a question. I'm Chris Pantelidis. Joseph, thank you for a very informative lecture.
Of course.
My question is, what can, I'm a professor, so what can I do? And I teach concrete here. When I'm teaching, how do I transfer this knowledge to our students? Because the students now are familiar with sustainability, but I can't go and write a formula on the board and say, hey, that's how you calculate sustainability. It seems like this topic deserves a lot more attention in our curriculum.
I absolutely agree. And so one of the approaches that I've taken is also having that apples to apples comparison. Like when, for instance, when I showed the comparison of each of the different pipe types and the resulting emissions that come from those. I think a big part of teaching sustainability, especially within the concrete world, is showing that, you know, while there is room for improvement, and many researchers are finding ways on how to do that, we can also show both the benefits of concrete, but also show what the alternatives would be as well. And so I think with this presentation and the report that comes along with it, I think that is one of the main approaches that we are taking. Does that answer your question?
Yeah, no, I think that's a good way to go, but we need to do more than just pipes. I think we're gonna have to do this for everything.
I absolutely agree.
Buildings, bridges, roads, everything that we are doing today, you're right, we have to answer about tomorrow.
Absolutely. I absolutely agree with you.
And also, like you said, you can't stop at the delivery of the project. You have to think what happens in 30 years or 50 years. And in fact, I do have a project that deals with corrosion of concrete. And how does the seismic performance change if you have corroded columns, for example? And these days, you know, we need to look at, and our center actually, Try Durali, is focused a lot on durability, life extension, because without knowing that, how are you going to do a correct resilience calculation?
Exactly. And I think that's I mean, even in my short career as an engineer so far, I've seen an incredible uptick in discussions on resilience and how it relates to sustainability. And I think, I mean, even just applying this discussion to the drainage world, which is where my career is centered, I think that's only a small step of what I can do to promote these theories and the necessary steps that we all need to take toward looking towards the future.
All right, thank you.
Yes, and thank you as well. You were exactly right. Any other questions that I can help answer?
I don't see any questions in the chat box. So I think we can go ahead and end our meeting, and just want to remind everyone to, when I send out the announcement that this is posted online, kind of addressing Chris's question, I think this presentation would be a great segue in any classroom to start this discussion, and like a really good beginning point. So you can address any questions to him once I send out his contact information. So thank you everyone for attending today. And thank you so much, Joseph, for your time. We truly do appreciate it very much. So
It was my pleasure.
okay, thank you everyone, and have a great day.